Hi, welcome to Mathematics with Tom. I am Tom, and today we are going to talk about the motivation for the central limit theorem. That is our topic for today, this motivation Oh, yes. My little beagle came to help. Here she is. Motivation for the central limit theorem. Okay. Now, a quick reminder of why this is important or where we're going to be going. Remember, what we've been studying up to this point is the normal distribution. We've learned its properties, that it's symmetric about the mean. We've learned how to use a table of z-scores, or maybe how to use the calculator, and we've learned that the area under the curve now represents the probability or the proportion of a population. So what if the problem, though, you should be asking is, well, what if the underlying distribution is not normal? Well, let's take a look. Our whole story today begins with a data set. So here it is. Here's our opening data set. Is 1, 3, 5, you know what, let's put a 7 on there as well, and 7, there we go. This is our opening data set, and I'd like to begin with drawing a relative histogram. Okay, so we start here with our axes. On our horizontal axes, we're going to put our data set. So it starts here at 1. So 1, 2, 3, 4, 5, 6, 7. We'll even go all the way to 8 if we wanted. And we'll number these. Now, a relative histogram, remember, then the vertical axis will be a ratio or a percentage if you want. So each data value only occurs once. There's 4 data values. Each one has a frequency of 0.25. Or if you wanted to write 1/4, that works as well. So in our histogram, really, we only have a bar over 1. So our class, we'll do this in this pretty yellow. Our histogram, as the first class, has boundaries from 0.5 to 1.5. Our second one from 2.5 to 3.5. And even if my line isn't perfectly straight, these bars all should be coming up to the 1/4 mark, from 4.5 to 5.5. And if I get ahead of you in this, just stop me. Just stop me and catch up. Remember that the act of you creating this with me is where the act of learning begins, in the act creation. All in the creation of the idea. Creation brings understanding too. So what I'd like to do is, let's now calculate, we're going to find the mean variance and standard deviation. Standard deviation for the data set. Okay, so remember this data set represents the population. That's a population of just 4 numbers. As a matter of fact, it's the first 4 odd numbers. That's our data set for today. So our mean, said we take the 1 and we add 3, and we add 5, we add 7. We're going to take that result. We have 4 values, so we would divide it by 4. Now we add 1 and 3, that's 4, plus 5 more, that's 9, plus 7, you get 16 fourths, which reduces to 4. Okay, that's the mean of our distribution. Now let's calculate the variance. Calculate the variance. And remember, we're using the population variance because that's the population, just those 4 numbers. So now we take the first value, which is a 1, and we subtract the mean of 4, and we square it, plus. Take our next data value, which is a 3, subtract the mean of 4, and square that, plus. We take the mean, the next data value, 5, minus the mean, and we square it, plus. Our last data value is 7. We subtract the mean of 4 and we square it. And then we're going to divide this. We're going to divide this by 4. By 4, the number of data values. So here we go. So 1 minus 4 is negative 3. We're going to square it to get positive 9. Plus, we have 3 minus 4. That's negative 1. We'll square it. That'll give us a positive 1 plus. 5 minus 4, that's 1. We'll square it, get another 1 plus. 7 minus 4, that's 3. We're going to square it to get 9. Take that value there. Divide it by 4. Now, if I add the numerator, 9 plus 1 is 10. And then we have another 1 plus 9, which is also 10. And remember that the associative property of addition says that you can add in different orders. So 9 and 1 is 10, 1 and 9 is 10. Add those 10s together, we have 20. 20 divided by 4, which is 5. So the variance, our variance, I'll just write that down here. Our variance is 5. And once you have the variance, the standard deviation follows. The standard deviation, remember, is the square root of the variance, which is the square root of 5. Now, you could rush out to your calculator right now and plug in the square root of 5, and we could write a decimal approximation of this never-ending, non-repeating pattern of numbers. But I think for the purposes of what we're doing today, it's more about discovery than it is about getting a numerical value. So let's keep the square root of mind at the forefront of our minds, square root of 5, sorry, at the forefront of our minds. Now, you might say that was a lot of work for a uniform distribution because we're studying normal distributions. So here we go. What we're going to do is now we're going to take all possible samples of size 2. Of size 2, then represent each sample by its mean, x bar. Okay. Oh, one last little note before we leave is notice this. Notice that if I was to grab my pretty yellow again, and if I called the first bar, if I took the area of the first bar and the area of the second bar plus the area of our third bar plus the area of our fourth bar. In other words, if I sum up my areas, this is the width of each one of these rectangles is 1. The height of each width of these rectangles is each 1/4. So this would be for the first one plus the second one, which again has a width of 1, a height of 1/4, plus the second rectangle has a width that goes, the third rectangle goes from, if I go 5.5 minus 4.5, that's where I'm getting my width of 1, times its relative frequency of 1/4, plus the final bar, the area of rectangle 4, which is also 1 times 1/4. Notice this is just 1/4 plus 1/4 plus 1/4 plus 1/4. That's 4/4. That is just 1. Just like the area under the standard normal distribution. The area of those rectangles is 1. Okay, I think we're ready. I'm going to go to a new screen. If you have room on your paper, stay on that page. Otherwise, grab another piece of paper and follow me as we take all possible samples of size 2. Here we go. So I'm going to write this. I'm going to write this as, oops, not like that. Let me change my color. All right, so I have my sample. And then its mean, x bar. And we're going to have a bunch of these, sample. And x bar. Here's a little, I'm going to go over here. How many samples will I have? Just to make sure we get them all or don't get too many. How many samples? Well, think about this. We're going to take samples of size 2. So each sample is going to have 2 characters in it. In the first spot, I could put a 1, a 3, a 5, or a 7. So there's 4 different things that can go in this first position. Then in the second position, you could put a 1, a 3, 5, or a 7 again. So now there's 4 different characters that could go in the second position. And then we have the law of multiplication that just says that 4 times 4, there's 16 samples if we do this correctly. Okay, that's our check. Here we go. So I'm going to be very systematic in taking my samples. My first sample, I'm going to start with a 2 in the first position, and then let's just run through the other possible characters. So I could have a 2. And then in my mean, well, I would say that 2 plus 2, then I average those, so I divide it by the number of sample, or number of data, which is 2. So 2 plus 2 is 4. Oh gosh, it's not 2 and 2, it's, you guys should have said something. Okay. All right, here we go. So we have a first sample, we're going to start with a 1 and a 1. And the mean would be 1 plus 1 divided by the number of data, which is a 1 and a 1. So 1 plus 1 is 2. Divide that by 2 to get a 1. Okay. And then again, let's leave a 1 in the first position, but now we'll have a 3. So then I have 1 plus 3. Divide that by 2. That's 4 divided by 2. That's 2. And let's just continue in this pattern. So 1, 5. 1 plus 5 is 6. Divide that by 2. The mean is 3. And then we'll 1, 7. So 1 plus 7, that's 8. 8 divided by 2 is 4. Now we've exhausted 1s in the first place, so let's go to the next number. That's a 3 in the first position. And then we'll run through the second position's all possibilities. Well, there's a 1. 3 plus 1 is 4. Divide that by 2. You could have 3, 3. That's going to be 3 and 3 is 6. Multiply it by a half, or divide it by 2 for 3. 3, 5. That's going to be 8 divided by 2. And finally, 3, 7. That's going to be 10. If I add them to multiply or divide by 2, that's going to be 5. And then let's continue this pattern. I'll continue working through this. You should as well. And here we go. So next one, we'll start with 5. So I'll go a little faster now. I have 5, 1. X bar is not 6. Maybe I shouldn't go fast. 3, 5, 3. X bar is 4. 5, 5. X bar is 5. 5, 7. X bar is 6. 5. Oh, I've exhausted my 5s. Oh, here we go. We're moving up now. So now I go to 7. 7, 1. It's 4. 7, 3. It's 5. 7, 5. It's a 6. And finally, 7, 7 with a mean of 7. There we go. Now let's make just a table of what we found. So let's write this. Let's write our sample mean now and our frequency. Before we go on, I want to make an argument for you, because you might think, well, why in the world am I representing each one of these data sets by its sample mean? And I'd like to tell you that it's probably more natural than you realize. It just hadn't been made apparent. For example, if a teacher comes back the day with a stack of tests to hand back to you, it used to be then the question would be, well, how did we do? In other words, what was the class average? So the teacher represents the class's performance based on the average score of the class. Here's another one that might make even more that might even be more apparent. An NBA team is required to have 12 players. So if you've ever been in an elevator with some members of an NBA team, it's hard not to notice one thing. They're tall. They're really tall. And so how do we describe the height of an NBA team? Very simply, the easiest way to do it, the most natural way to do it is say, oh, the members of an NBA team, the average height of the team is 6 feet 6 inches tall. So there again, we've decided we've taken 12 people, 12 players, and represented the group's height as an average. So believe it or not, it's a very natural way to represent a group. So let's continue. Our first average was 1s. And let's see, how many 1s do I have? I'll do it this way, 1s. Notice right there, I have just 1, 1. So it has a frequency of 1. Now I go to my next data value. Well, let's see. Let's go to 2s maybe. Well, notice if I look over here, there's a 2. And is that it? Oh, just down below a little ways there's another 2, and then it looks like they just get higher. So 2s have a frequency of 2. Okay. What about 3s? Well, let's see. Here's a 1, 2. Is that it? Oh, I've got another one. 3. 3s have a frequency of 3. 4s. There's a 4, 1, 2, 3. Any more? Oh, 4. There it is. So the average of 4 occurred 4 times. Okay. Let's do a pink data set. So our next is 5. So here's a 5. And then, got another 5, and if I'm looking down below, and down below a couple more lines, there it is, there's another 5. So the 5s occurred 3 times. And then let's go on to 6s. 6s, here's one. There's a 6. Gosh, I've almost used up all my values. There's another one. So the 6s have a frequency of 2. And finally, let's do this, use this icy blue color. I like this one. Is 7s. Notice our 7s. That's kind of hard to see. Make it this one. 7s. 7s occur just 1 time. And that's our frequency distribution for our sample means. So the first thing I want to do, there's 3 things to do. So here, 1, make the histogram. 2, we want to find the mean. Find the mean of the sample means. And it has a unique notation. It's described as mu, just like the population mean, but this time it's mu of the sample means, and so that's the notation that we're going to use. And finally, the third thing, number 3, is find, well, I guess there's 4. Once you find the variance, you have the standard deviations. I was thinking of those as one step in my head, but it might be 2 depending on one's perspective. So we're going to find the variance and standard deviation of the sample means. And the sample means, and it has the notation is sigma squared with an x bar on it. This is the variance of the sample means, and the standard deviation is sigma x bar. And so I'm going to put respectively, meaning that the order here at the beginning of the sentence is the order of the symbols at the end of the sentence. Okay, there's 3 things that we're going to do. So let's do the first one. Let's make our histogram. So let's go back to original histogram. I think it makes it more impactful. So I'm going to return to where we began. The first, and we're going to overlay our histogram. So let's do this. Let's do this in this. Need something that contrasts nicely. We'll do this pretty blue here. Okay, so the first, if you recall, the first sample mean was 1, and it had a frequency of 1 out of 16. Well, 1 out of 16 is 1/4 of 1/4. So if I look at my vertical axis on the left, I have 1/4. So if I cut it in half, this would be 1/2. If I cut that in half, that would be, oh no, 1/2 of 1/4, that's an 1/8. Goodness, you guys should say something. It's an 1/8, and 1/2 of an 1/8 is a 16th. So now we're looking at units of 1/16, 2/16, 3/16. There we go. So the first data value, 1, has a width of 1, but it only goes up to 1/16. The next one, 2's occurred twice, 2/16 of the set. So that bar now, I'm going to do this with a thicker pen too. So now my bar is going to go up to 2/16, over to 2.5, and then back down. Well, 3's occurred 3/16 of the time. So I'd go from 2.5 up to 3/16, over to 3.5, back down. Our boundaries are still 1 unit wide. And 4, that occurred four times, or 4 out of 16. So look at this. And then our 5s, they occur, there's 3 of those, so it has a frequency of 3/16. The 6s, those occurred twice, so 2 out of 16. And finally, the 7s occurred only once, so 1/16. And that is what we get. Notice this is starting to look more normal. And at the very end here, I'm going to show you what happens if you just take all possible samples of size 3, how much more normal looking it begins. Now, let's return. I'm going to go back. Step 2. Step 2 says find the mean of the sample means. Okay, let's do that. We can do this. So the mean the mean of our sample means? Well, so let's do it this way. We have the ones, and it has a frequency of 1 plus. Our next sample mean was 2, and it had a frequency of 2. And remember, you could write 2 plus 2 because the 2's occur 2 times, or you could 2 plus 2 is the same as 2 times 2. So like the 3's, I could write 3 plus 3 plus 3, or I can just write 3 times 3 plus. And I could have 4's, and they occurred 4 times. Plus, then I had my 5's, those occurred 3 times. Plus, I have my 6's, those occurred 2 times, plus my 7's, which occurred once. And then I want to divide this. I want to divide this by 16, by my total number of sample means. So let's do this. 1 times 1 is 1, plus 2 times 2 is 4, plus 3 times 3 is 9. 4 times 4 is 16. 5 times 3 is 15. 6 times 2 for 12, plus 7 times 1. We're going to divide that by 16. Okay, now if you have a calculator, this is a good time to use it. My mental math has been wrong at least once. So 1 and 4 is 5, plus 9 more is 14, plus 16 is 30, plus 15 for 45. 45 plus 12 is 57, plus 7 more is 64. Whew. And 64 divided by 16, this is 4. Wait a minute. Whoa, wait a minute. Didn't we see a 4 before? If you recall, look at this. There it is, right there. Right over here. Notice that the mean of the data was 4. But we just calculated the mean of the sample means, and we got 4 again. Is that coincidence? No, that's not coincidence. That's one of the beauties of the central limit theorem. So in other words, when I get a 4 from the mean of the sample means, that is exactly the same as the mean of the original population. That was step 2. Step 3, well, you can see what's going to happen on step 3. We need another page. So let's do that. Let's go to our next page. Now, I'm going to write these up here. We had the mean of the original data set was 4, and that was equal now to the mean of the sample means. And if you recall, our original variance was 5, and our original standard deviation is the square root of 5. Okay, here we go. Now we're going to calculate the variance of the sample means. So what we do is this. We say, okay, our first data value was a 1. We subtract the mean of 4. We're going to square it, and then it occurs 1 time, so I'm going to multiply it by 1 plus. The next data value were 2's. Subtract the mean of 4, we square it, and we multiply by the number of 2's, which there were also 2, plus. Our next data value, next sample means were the 3's. We subtract the mean of 4, and this, when I say we subtract the mean, we're subtracting, well, it doesn't matter, but we're using the sample mean, which just happens to be the same as the population, we're using the mean of the sample means, which is the same as the mean of the original population. So we take 3, subtract 4, we square it, and we multiply it by 3 plus. Our next sample means were the 4's. Subtract the mean of the, which is 4, square it, and multiply it by its frequency of 4 plus. Our next data value is 5's. So we take 5 minus 4, we square it, and we remember that the 5's occurred 3 times, plus. Our next data values were the 6's. We subtract 4, square it, multiply it by its frequency of 2, plus. Our last sample mean was 7. Subtract the mean of 4, square it, and its frequency was 1. Take all of that, and we have to divide this. We have to divide this by 16. This is going to be good, I think. I think so. I'm going to do this in 2 steps, so let's walk through this. 1 minus 4 is -3. We square it, it becomes 9. Multiply it by 1, and we have 9 plus. 2 minus 4 is -2, but you square it to get 4. Multiply it by 2, and you get 8 plus. 3 minus 4 is -1, but we square it, it becomes +1. Multiply it by 3. 1 times 3 is 3 plus. 4 minus 4 is 0. We square it, it's 0. And we multiply it by 4. 0 times 4, that is 0. I'm going to write it just so that we can keep track of all of our pieces here. Next term is 5 minus 4. That's 1. Square it, it's 1. Multiply it by 3 for 3. Plus. 6 minus 4 is 2. We square it, that's 4. Multiply it by 2, that's 8. Plus. 7 minus 4 is 3. Squared is 9. Times 1, it's still 9. Take all that, divide it by 16. Okay, here we go. Mental math. 9 and 8 is 17. 3 more is 20. Plus, we have another 20. That's 40. So we have 40 over 16. Now, at this point, you could put this into your calculator and you'd get a number, but this exercise is not about that. This exercise is about understanding. Notice that 40 over 16 is the same as 8 times 5 over 8 times 2. So the 8s would cancel, and we're left with a fraction. The variance is 5 over 2. Whoa. Do you see this? Look at what happened. Where's that 5? That 5 is the same 5 as from the original variance. So now, what about that 2? Where did that 2 come from? Is it important? Yes. Remember, we took all possible samples of size 2. In other words, that 2 is n. It's the size of our samples. So then, in other words, and so there it is. We can say the variance of the sample means is equal to the original population variance divided by n. And if we come up over here, we can say then that this, if I take this, the standard deviation for the sample means, well, remember that this is the square root of the variance of the sample means, but we just said that this becomes in the square root of, well, we put in, notice that this term is that whole fraction. It's the original population variance divided by the sample size. Well, it may have been a while since you've worked with square roots, but the square root of a fraction is also the fraction of square roots. So this is the square root of the variance divided by the square root of the sample size. And we already know that the square root of the variance, that's the standard deviation divided by the square root of n. Whoa. Let's sum this up. The central limit theorem is one of the most powerful theorems in mathematics when you think about what you just did. You took a uniform distribution, and then you found its mean and its variance. Then you took from that all possible samples of size 2, and you found that the mean of the sample means is the original mean, and you found the variance to be of the variance of the samples to be almost the same. It only changed because it was divided by the size of the samples. And now all that work that you spent understanding the normal distribution can be applied to the distribution of the sample means. And here's the idea, that as the size of the samples increases, say you sampled all possible groups of 4 or 16 or 25, what happens is each time you do that, the width of those histogram bars get narrower and narrower and narrower, and they get closer and closer together, and the amount at the ends gets smaller and smaller, and the amount of the middle gets larger and larger. The liberty of finding all possible samples of size 3, taking all their means, and I have this graphed for you. Here's the original uniform distribution, and then if you take all possible samples of size 3 and go through the process we just completed, you end up with this new histogram. And notice that the amount in the tails is very small, and then most of the material is in the middle. And as our size of our samples grows larger, the rectangles get smaller and smaller, and fairly soon, if you have maybe a nice steady hand, you could draw these, and you get a picture. You get a picture that would look like this. If you were to continue this experiment as n gets larger and larger. I hope that helps, and thanks for watching.